Hey everybody, this is our lecture on section 2.6 on quadratic surfaces. Now, this section is not on the syllabus. The syllabus skips over section 2.6, but really, so many of the examples that we're going to do later use the information in section 2.6, so I thought an abbreviated presentation of this section is called for. And the email I sent you has the assignment, the homework problems to do in section 2.6. So here's a review of 2D conic sections. An ellipse has the following standard form, centered at the origin, has the following equation in standard form. All right, and that's this guy, x-axis, y-axis. I got it backwards. This is the x-axis and y-axis. And these points here are positive a, minus a, positive b, and minus b. All right, perhaps you remember that one. There's also the hyperbola, which you may have seen already, but maybe you forgot about it. Let's take a look at it. I mean, it's worth mentioning it again. So the hyperbola centered at the origin has this standard equation, or right, plus here, minus here, or minus here, plus here. And those are two different hyperbolas. I'll show you the difference between them. Let's do this one first. So on your y and x axes, again, pick out a and minus a on the x-axis, b and minus b on the y-axis, and you've got this sort of guiding rectangle here. Okay, that's not part of the hyperbola, but it's there to help you draw it. We put it there to help you draw it. And then on this rectangle, you've got these diagonals. Diagonal lines going through the corners of those things. And then if x is positive and y is negative, the coefficient of x is positive, coefficient of y is -1, then the hyperbola opens along the x-axis. And it's got these slanted asymptotes here, given by this box. And, that's the hyperbola for this equation. For the other equation, where we switch the positive and negative around, it opens up and down rather than left and right. Minus plus, so get rid of those. So here you have this same guideline box and guidelines, but the hyperbola opens this way. Opens up along the y-axis. Okay. So now, using those two-dimensional conic sections, we have these things called quadric surfaces in 3 dimensions. All right, so some 3 variable surfaces built up from conic sections. So, for example, okay, let's sketch the surface given by all points x, y, z, satisfying the equation x squared plus y squared minus z squared equals 1. Okay? All right. So what we're going to do, okay, it's a 3 variable equation. But what I want to do is I want to reduce it to a 2 variable equation. Okay, we reduce to a 2 variable equation by just setting z equal to some number. Okay, so let z be equal to just some fixed constant. It's no longer variable, it's constant. Then x squared plus y squared minus z squared equals 1 becomes, well, I'm just changing z to k, but it's a constant, becomes this, right? Where this is just constant. Positive constant, in fact. Right, so now if I look at the plane z equal to k, so in the plane z equal to k, right, what do we have? I have a circle. X and y form a circle. So the equation forms an ellipse, or a circle, it's just a circle in this case, forms a circle in the plane z equal to k. All right, so in 3D space, it looks like this. Here's the plane z equal to k. All right, and then x and y form a circle, and there it is. A circle of whatever radius it might be. Okay, so we've got in the planes parallel to the xy plane circles. So now the question is, what is the silhouette that all those circles make? Okay, in order to see that, okay, let's let x equal to 0 and let y equal to 0. Again, we're taking the 3 variable equation and changing it to a 2 variable equation. We'll do so, let x equal 0 and let y equal to 0 and see what happens. All right, so let x equal to 0 and x squared plus y squared minus z squared equal to 1 becomes, let's let y equal 0 first. No, x equal to 0. Becomes y squared minus z squared equal to 1. That's the hyperbola that we were just talking about. Here, the guideline is just the square box. Right? Opening, so make that the z-axis, this the y-axis. Right, and we have the hyperbola like that. So that's the silhouette. You have a hyperbola in the YZ plane, right, that tells you what shape the circular surface is going to take. Similarly, if we let y equals 0, okay, then x squared plus y squared minus z squared equal to 1 becomes x squared minus z squared equals 1. Right, and then you have a similar picture. So putting all that together for x, y, z space, right, here's x-axis, y-axis, z-axis. Here's that hyperbola in the yz plane. You also have that hyperbola in the xz plane. I think I'm going to leave it out. I think this is enough for the drawing. And now, parallel to the xy plane, you have circles. And then the radius of those circles is given by, this hyperbola. So there's your surface. That's called a hyperboloid of one sheet. Right, and you can add in a few more if you want. I don't know. So make it look nicer, maybe make it look worse. Yeah, I'll take those out. Okay, let's try another one. How about x squared minus y squared minus z squared equals 1? So here I just changed that plus to a minus. All right, so let's see. If I let x be a constant, right, then x squared minus y squared minus z squared equal to 1 becomes k squared minus 1 equals y squared plus z squared. So as long as k is bigger than or equal to 1, right, so for k bigger than or equal to 1, in the yz plane, I've got circles again. Y squared plus z squared equals something, right? That's a circle centered at the origin. Okay, so I've got that. And now, what does the silhouette look like, right? So here's x, y, z space, right? And here's the plane, x equal to k. And then I've got this circle inside that plane, x equal to k. Right, centered on the x-axis. So now I just need to know what the silhouette of the surface is looking at it from the side over here. Right, so I can get a better idea of what that looks like. So let's let z equal to 0. Right, I'll get the silhouette in the xy plane. If I let z equal to 0, then I got x squared minus y squared equals 1. Right, that's the hyperbola opening up along the x-axis. Right, and then if I let y equals 0, well, if I let y equals 0, I'll get a similar picture. Right, then this becomes x squared minus z squared equals 1. Right, so now putting all these things together here, what do we get? Right, here's x-axis, y-axis, z-axis. Here's the hyperbola in the xy plane. I'm not sure it looks too good. Let's see. Okay, it's good. And then I've got these circles. right? So that's that hyperboloid again, but this time it's facing, well, it's centered on the x-axis. Um, oh, excuse me, that's incorrect. I drew this the wrong way. That hyperbola, it opens up along the x-axis, not along the y-axis. Opening up along the x-axis in the xy plane looks like that. And then it opens up, right? This is x equal to 1 over here, xy plane, and then you have a similar copy back here. And now I can put those circles on there, and this is called a hyperboloid of two sheets. There it is. Okay, so I drew the hyperbola, and then parallel to the YZ plane, right, I've got circles. Parallel to the YZ plane, I've got circles, and then the hyperbola gives me a good silhouette for how those circles are growing and shrinking and how they look next to each other. Okay, so I've got this picture here. Let's try some more. So a lot of the stuff that we're going to be doing later, when we start doing differentiation, integration, in three-dimensional space, a lot of the surfaces that we do as examples come from these things. So I mean, it's definitely worth talking about. So here's a neat one. Z equals square root x squared plus y squared. So now let's be a little quicker about it. Okay, if I let z equal k, right, just a constant, then I have k squared equals x squared plus y squared. So in the xy plane, or in the plane z equal to k, parallel to the xy plane, we've got circles. Again, you don't have to be specific about the radius. You don't have to be specific about the radius, but there it is. We've got these circles. All right, and then if I let x equal to 0, so that I'm looking in the yz plane, I have z equals square root y squared. So z equals what? Not y. Z equals what? Not y. Z equals absolute y. Y could be negative, right? The square root of negative 3 squared, right, is square root of 9, which is 3, not negative 3. The square root's always positive. So in order to sort of fix that thing, you have to put an absolute value there. And then if y is equal to 0, we've got the same thing. Right? So what does this picture look like in the yz plane, where x is equal to 0? Z equals absolute y. Well, that looks like that. Same thing in the xz plane. So putting these things together, what do we get? All right, so this is xz. We also have that. So putting these pictures together, what do we have? This is x-axis, y-axis, z-axis. Here's the yz plane. I've got that. And then in the xz plane, I've got the same picture. And then I have circles parallel to the xy plane. So I've got this nice cone. There we go. Like that. All right, so that's a cone. where the angle here, right, is 45 degrees. So that's a nice important surface. And then one very similar to that. So this was z equals x squared plus y squared. Something real similar to that. Instead of the square root, if I just wrote z equals x squared plus y squared, for z equal to k, again, we get circles. And then for y equals 0, we have z equals x squared, right, which is, x, z. And then for x equals 0, we have z equals y squared. So again, that's the standard parabola. Right, so putting those together, what kind of picture do we have? X, Y, Z. Here's the YZ plane. Make that parabola. Do the same thing in the XZ plane. Make that parabola. Let's make that a little taller. And then fill in with circles. So instead of a cone, we have this thing called a paraboloid. Right? So that's pretty neat. You know, I mean, just by knowing how to draw circles and parabolas, circles and hyperbolas, or ellipses and hyperbolas, or ellipses and parabolas, what did I say? Hyperbolas, then, you know, you can draw these quadric surfaces because they're just ellipses or circles framed by these other curves. Okay? So we'll talk more about quadric surfaces throughout the course, but that's just a quick introduction to them. Okay? So that is the lecture for this section.